Hey everyone, welcome back to Calculus 2. This is going to be lecture 22 of the course, and in this one we're going to discuss improper integrals. Alright, so let's go ahead and get started. And we'll call this section 3.7 improper integrals. Okay, so by the word, when we say the word improper, what do we mean? We just mean kind of unusual. Right? I don't think there's anything improper, although these do technically fall outside of what we would call an integral typically, right? So the definition of a definite integral, right? So let's talk this through. The definition of a definite integral, right? A to b f of x dx. Okay. There's a couple requirements here. First of all, it's going to require the interval a, b to be finite. Right, so a and b are assumed to be, finite numbers when we're talking about a definite integral. Okay. Another thing that we'll be in violation of here briefly is the fundamental theorem of calculus. So if you remember back to the fundamental theorem of calculus, this is going to require f to be continuous on AB. Okay, so two things here of key import for this section, right? First thing is when we are talking about integrating over, when we're talking about a definite integral, the region of integration has to be finite, right? That's just by definition, right? And if you think back to how we constructed those definite integrals, we use rectangles and a partition, and et cetera, et cetera. And so all of that mechanism requires AB to be finite, right? The second thing is that we said, hey, look, to use the fundamental theorem of calculus, it's going to require f to be continuous on AB, right? Meaning there's no discontinuities, there's no gap, there's no sort of infinite gaps in the function or some asymptotic behavior, any of that on f over the region of integration, right? So those two pieces are what we typically run into when we're dealing with improper integrals. So in this section, we're going to study basically a procedure for evaluating integrals that do not satisfy these two requirements. Okay, that do not satisfy these two requirements. So we're going to look at integrals like the first thing we'll look at is situations like this, where you've got a to infinity of f of x dx, or infinity to b of f of x dx, or negative infinity to infinity of f of x dx, right? Those kinds of things. So that's the first thing we'll look at, first kind of improper integral. And then the second kind of improper integral is going to be ones where there's a certain number of discontinuities over the region of integration, right? So what if I have this function, it looks like this, and I want to integrate from a to b. So meaning I want to know what this area is, but I have asymptotic behavior right in the middle of the region. How can we deal with that? How can we integrate function like this? Okay, when you have an infinite discontinuity here. Normally we would say, hey, this is outside of what we can do, but thinking of it as an improper integral is going to introduce a range of techniques. Okay, so these kinds of things are called, this is what we mean when we say improper integral. You know, and so sometimes when people hear the word improper, they think, oh, bad. No, they're not bad. They're actually extremely fascinating. Some of the more interesting integrals you're ever going to come across. So, okay, so let's talk about this one. Let's start with this idea. So let's consider the function f of x equals 1 over x squared. Okay, and let's just plot this thing on the positive x-axis. So it kind of comes down and looks like this, right? Right, as x gets larger, then the ratio gets smaller, 1 over x squared. All right, so let's say we've got 1 here, and then we've got some value b out here. Okay, now this area here can be captured by the integral 1 to b, whatever b happens to be, of 1 over x squared dx. All right, we could quickly do this. This is negative 1 over x from 1 up to b, and so we get negative 1 over b plus 1 over 1. Right, and so we can clean all that up, and this looks like 1 minus 1 over b. Right, that's the area. Right, so we can interpret this 1 minus 1 over b. We can interpret this as the area between 1 and b of this graph above. Okay. All right. Now, what happens when we take the limit of this b as b goes to infinity? Okay. Right, so what happens when we move this upper bound of integration off to infinity? Well, let's look. Right, let's do that exercise. And so this is going to kind of set up the first type of improper integral and how to deal with it. So if I look at this 1 to infinity of 1 over x squared dx, one nice way to write this would be to, instead of writing infinity as the upper bound, because we can't, in order to evaluate this integral, we're going to have to plug those upper bounds into, you know, whatever function we get as, you know, when we calculate the integral, but we can't plug infinity into any expression, right? So what we can do instead is we can convert this to 1 up to b and write the limit as b goes to infinity in front. Okay, because we're never going to be able to plug infinity in, but we can plug b in and we can evaluate an expression involving b as b goes to infinity. Right, so that's going to be kind of our approach to dealing with integrals like this. Right, so this is going to be equal to the limit as b goes to infinity of, right, we calculated this integral just a moment ago. This is 1 minus 1 over b, right, plugging all the bounds in and doing all the work. Right, now what happens to this limit? Right, now as b goes to infinity, what happens here? Well, this is going to be equal to basically 1 minus 1 over infinity, so 1 minus 0, so 1. Okay, so this tells us that the area under the curve of f of x equals 1 over x squared between, well, I'll say on the interval 1 to positive infinity is equal to 1. Now that's kind of remarkable, isn't it? Right, that's kind of remarkable. If this is the first time you're seeing this, you may be saying to yourself, what? Hold on a second. Right, so you've got this function f of x equals 1 over x squared. Right, 1 is going to be on here somewhere. Whether that's a good picture or not, I don't know. But right, so what this basically says is that, look, the area from 1 all the way up to positive infinity is a finite number. That is remarkable in many, many ways. right? You're taking an infinite, like this goes all the way up to infinity, right? Forever in that direction, right? And forever in that direction, the curve is non-zero. It's not like it becomes zero at like 2 million or something. It's always non-zero. It's always above zero. It's greater than zero, right? But it shrinks very, very rapidly as x starts to get large, right? The amount of area you're adding at each interval, at each unit, as you move off to infinity is a tiny, tiny area. And that what basically is happening here is that the rate of decrease of the area that you're adding is rapid enough that the whole area converges to not only a finite number but the number 1. So this area is a finite number and is equal to 1. Okay, so that is amazing. So this is an infinitely long interval, but and this curve is greater than 0 along that entire interval, but the entire area is equal to 1. Okay, so this is kind of why I say these improper integrals are some of the most interesting integrals you're going to come across. Okay, so let's go ahead and kind of define let's write down how to deal with improper integrals with infinite integration limits. Okay, and so there's really 3 variations: improper integrals with infinite integration limits. Right, so there's kind of 3 scenarios that can occur. Right, the first one is what we just looked at, right, where you've got some finite lower integration limit but an infinite upper integration limit. Right, and that's the case that we just looked at, and so the way we want to deal with that is we want to take the limit as b approaches infinity of the integral from a to b of the function. Right. Again, just to reiterate, the reason we do it this way is because we can't plug infinity into an expression and evaluate it. And when we do it, when we evaluate a definite integral, that's what we have to do, right? We have to plug b into the integral, and then we have to plug a in, we subtract the 2 to come up with the area, right? We can't plug infinity in, we can plug b in, and then we can take the limit as b approaches infinity. Right, so that's what we just did. The other another scenario that can occur, of course, is when the lower bound is infinite, like so. And we're going to run the same operation there. We're going to say, okay, we can't evaluate negative infinity in any expression, so we'll take the limit as a goes to negative infinity of the integral from a to b. Kind of the reverse operation, right? Okay, and then the other scenario is where you have both upper and lower integration bounds are infinite, right? So I have something like this. Right, I want to know basically I want to sum across the entire real number line, right, for some function. Well, then we kind of break it into 2 pieces. We consider this guy from negative infinity up to some finite value c, plus the other end, right? Infinity from c up to infinity of f of x. Okay, and then each of these, of course, we use 1 and 2. For 3, right? So basically this integral here is basically case 2. We got negative infinity up to some value, negative infinity up to some value. This one over here is case 1, so you got some value c up to infinity, some value up to infinity, right? So basically we can break the range down into 2 pieces and then sum the 2 pieces separately using 1 and 2. Okay? Perfect. Let's do another example. We kind of did an example, like a motivating example. Let's do another one where we use this technique. let's evaluate the integral from 1 up to infinity of 1 over x dx. So similar to the previous example, not exactly the same though. I think you'll see they're quite different in reality. So integral of 1 over x dx, that's going to be equal to the limit as b goes to infinity of the integral from 1 up to b of 1 over x dx. And that's the limit as b goes to infinity of, now what is the integral here, 1 over x? Well, that's the natural log of x, isn't it? Natural log of x, and then that's from 1 up to b. And so we have the limit as b goes to infinity of, and this will be natural log of b minus natural log of 1. And the natural log of 1 is just 0, so this is the limit as b goes to infinity of the natural log of b. Okay, and so we know that the natural log will increase as b increases, and so this is going to be infinite. Okay, so in this case, this limit, this integral here produces an area that is infinite, right? So it's interesting. So that it's interesting that this area is infinite while the previous example was finite. Okay, now the previous example was 1 over x squared, wasn't it? Right, so let's kind of write this out here. So 1 is 1, and at when x is equal to 2, 1 over x squared is a fourth, right? So it's down here. And when x is 3, 1 over x squared is a ninth, so it shrinks very, very rapidly here. Okay, so this is f of x equals 1 over x squared. Now the one we just looked at was 1 over x, so it would be 1, 1, and then 1/2, and then 1/3. So it's 1/3, it's about there, and then 1/4, right? So this one is, I mean, they look so similar, right? Now clearly, we all know, right, just because we can kind of reason about this, this one is going to be quite a bit closer to the x-axis at each tick, right? You can kind of see that in the early days, but if we were to blow this up, really zoom in on this, we would see that this one is going to get closer to the x-axis much quicker than this one, right? Like imagine the value of 50,000 in here. 50,000, 1 over 50,000 squared is a lot smaller than 1 over 50,000, right? So clearly this is going to go to 0 much quicker than this one, right? And it's that rate of decrease, that rate of approach to 0, which makes this area finite, or this area is equal to 1, whereas this area is infinite. It's that rate of approach, what we'll actually call convergence in the next couple sections when we start looking at this closer. It's that convergence rate that really kind of determines whether you end up with a finite area or an infinite area. Right? For now, it's going to have to remain a little bit of a mystery. Right? We have to delve into convergence and talk about series and sequence and all that. And then even still, there'll be more work to do to really get at this issue. But suffice it to say, this is no fluke. Right? The area truly is infinite under this curve, whereas it's finite under this curve. They look an awful lot alike. And you might say to yourself, when I get infinitely far out on this, it doesn't matter. They're both really small, but it does matter. Remarkable. Okay. Very good. Let's take another look. Let's take another example here. Let's evaluate the integral from 0 up to infinity of e to the negative x. Okay, so similar setup, 0 to infinity, e to the negative x dx. Let's pull in a limit here. We'll let b go to infinity. So this will be 0 up to b of e to the negative x dx. Okay, and so it's the limit as b goes to infinity of, now what's this integral? Well, it's negative e to the negative x from 0 up to b. So the limit as b goes to infinity of, now what do we get here? We get negative e to the negative b, and then minus negative e to the 0 power, so that'd be like minus a negative minus plus 1, right? Now what happens here? Well, as b goes to infinity, this negative e goes to negative infinity, right? So e to the negative infinity, this whole thing's heading to 0, isn't it? Yeah, so this is going to be equal to 0 plus 1, which is just 1. So here again, we've got a finite area, even though our integration range is infinite. Very, very cool. Let's take a look at this one. So from 0 up to infinity, and then the integral is 1 over x squared plus 1. Okay, so we'll set it up just like before. From 0 up to infinity, 1 over x squared plus 1. Let's bring in a limit. Limit as b goes to infinity of the integral from 0 up to b, 1 over x squared plus 1. Now, what is this integral? Well, this is u squared plus a squared, isn't it? 1 over u squared plus a squared. So that means this is the arctangent, right? So this is arctangent of x from 0 up to b. Okay. And so this would be the limit as b goes to infinity of arctan of b minus arctan of 0. Okay, now what are these things? Well, arctan of 0 is 0. Arctan of b, well, that guy there heads off to pi over 2, actually. And so this would be equal to the limit as b goes to infinity of the arctangent of b, which is pi over 2. Okay. All right. So that one. So what do we remember? Kind of like what this means here. So let's draw in these functions here, because these are kind of weird functions. So 1 over x squared kind of looks like this. Right? It sort of looks like this. It kind of comes down like so. And this is, of course, 0. Right? So we're interested in the integral of this entire region here. This is 1 over x squared plus 1. Okay. And so, yeah, you can see here that obviously when x is equal to 0, this is equal to 1. Right? So that's 1. And then as x grows, the ratio shrinks down. So sort of similar to kind of like what we saw with the 1 over x squared, except the plus 1 makes this a little bit different. Okay. And then when we integrated here, we ended up with the arctangent. Now, if you recall what the arctangent looks like, the arctangent looks like this. So probably people remember what the tangent looks like. But the arctangent is basically going to be the tangent sort of on its side, isn't it? Right. So this would be negative pi over 2 here. And so we're going to have sort of this asymptotic horizontal asymptotes here. And so the arctangent is going to go like this. Right, so as you know, you can see here, as b goes to infinity, right, as you know, the value of that you're evaluating arctan, it goes to infinity, then this is going to tend towards this horizontal asymptote of pi over 2. Right, and the implication, of course, is that that is also the area under the curve of f of x equals 1 over x squared plus 1. Okay, so kind of a tricky one to think about, but yeah, very, very interesting. You can see sort of the connections between some of these guys. So it's interesting. This value here is pi over 2, right under the curve of this function. It's pi over 2. It's a very important constant in the world of trigonometry, and obviously it comes from the fact that this integral is arctan. Okay. All right. What about an example where the upper and lower bounds are infinite? Let's do one of those. We haven't talked about one of those yet. So let's evaluate the integral from negative infinity up to positive infinity of e to the x divided by 1 plus e to the 2x. Okay, now let's see what this looks like. Okay, so if I've got my xy axis like this guy kind of comes up to a peak and then heads back down. Totally symmetrical about the y-axis. And so what we want to know is, what is this area under the curve all the way from negative infinity to positive infinity? Is it finite? Is it infinite? Let's find out. Okay. So we'll start by let's rewrite the integral here, and then we're going to have to break it up, aren't we? We're going to follow the example that follow the rule that we kind of established early on. So we're going to, find some value in the middle. 0 is the most convenient value. We'll say this is the integral from negative infinity to 0 of e to the x over 1 plus e to the 2x plus the integral from 0 to positive infinity of e to the x over 1 plus e to the 2x. Okay, so from negative infinity up to positive infinity, we just broke it into two pieces. And now what we're going to do is we're going to plug in some, because we can never plug in negative infinity or infinity, so we're going to plug in an a and a b instead. Okay, and so this is going to be the limit as b, one second, I wrote this down. This is going to be the limit as a goes to negative infinity of the integral from 0 to a of e to the x 1 plus e to the 2x dx plus the limit as b goes to positive infinity of 0 up to b of e to the x over 1 plus e to the 2x dx. Okay, right? So just kind of plugging those two pieces in. And then we can evaluate these integrals, right? So let's see, this is a to negative infinity. And so what do we get here? Well, there's a little bit of work to be done here. You can use substitutions here. And basically what you'll find is that this integral here is the arctangent of e to the x. And that's from a up to 0. Okay, just take, you can pull this off to the side and just take a second and see that. And then this one over here, this is the limit as b goes to infinity. And over here, it's also the arctangent, obviously. Right? It's the same function. Okay, and then this is from 0 up to b. Okay. And so, have that, we can plug in our endpoints here. Okay, and so what we get is the limit as a goes to infinity. Now what is this? Well, when we plug in e to the 0, we get this pi over 4. And then it's minus the arctangent of e to the a power. Okay, and then plus over here, the limit as b goes to infinity. And when we plug that in, we get, again, the arctangent of e to the b power minus pi over 4. Okay? So no problem there. Okay. And so we can kind of pull some of this apart. Let's just do that quick. So we've got pi over 4 on the outside here, minus this first limit, plus this limit, b to infinity of arc tan e to the b, and then of course minus pi over 4 on the outside there. So these two are obviously going to undo each other. All right, but what's happening in the middle here? So what's going to happen in the middle here? Well, looking at this first one, right? So a is going to infinity. Oh, actually, I think I dropped one of these. One of these is going to negative. This one's going to negative infinity. Sorry. Okay, so that's going to negative infinity. So notice here for this first one. So note, let's kind of write down what's going on here because it's going to be a little bit tricky. So e to the a, right? What does this do? Well, this is going to go to e to the negative infinity, right? So as a verges the negative infinity, this becomes e to the negative infinity, which is going to be equal to 0, which goes to 0, we should say, as a goes to negative infinity. Okay, and so what does that mean? All right, so this piece here is going to 0, which means the arctan is going to 0 as well, right? So you've got the arctan of e to the a is going to the arctan of 0, right? Which is, hold on one second, which is equal to, let's see here, which is going to go to pi over 2. Oh, sorry, it goes to 0, sorry. Okay, all right, so sorry about that. So basically you just have to kind of reason this through. So e to the a, as a goes to a negative infinity, e to the a goes to e to the negative infinity, which is 0, right? Goes to 0. So that means this term here, this piece here goes to 0. Arctan, when arctan goes to 0, this whole thing is going to go to 0. So that whole thing goes to 0. Okay, now what about this other piece? Well, e to the b, so notice b is going to infinity. So e to the b is going to e to the infinite power, which is obviously going to be valued going towards infinity as well. So that means that the arctan of e to the b is going to arctan of, basically infinity, right? It's growing to without bound. And so we saw that this is going to go to pi over 2. Right? We saw that on the previous page, right? Let's remember what that looks like, right? So here's arctan's function, right? As b grows without infinity, say that's b, then the value of arctan gets closer and closer to pi over 2. So that's all we're saying here as well. So this is going to pi over 2. Okay, so this is all kind of side calculations. And so that means that we basically have pi over 4 minus 0 plus pi over 2 minus pi over 4. So the whole thing is pi over 2, isn't it? Okay. The whole thing basically is equal to pi over 2. So let's recap that. So that basically means that this integral, negative infinity to positive infinity, of e to the x over 1 plus e to the 2x is pi over 2. Nice. Very nice. Okay, so that's kind of the what we've established. And then this function, of course, it looks a lot like a bell-shaped distribution, like from probability theory, if you've seen those. It's a little bit like the normal distribution, actually. Right, so it kind of looks like this. And what we're saying is that this curve, the area above the x-axis between this curve on the entire real line is pi over 2. All right. Okay, Perfect. So that's a good place to stop that. Now let's switch gears to the other type of improper integral that we can come across. All right, so the second type of improper integral. So remember, this is one that has an infinite discontinuity at or between the limits of integration. So let's write that down. The second basic type of improper integral is one that has an infinite discontinuity at or between the limits of integration. Okay, so this is the second kind we want to look at. Right, and so, there's a couple of examples we could whip up. So here's an example. Right, so say we want to integrate from 0 up to some number, we'll just say 1. Right, you got some function that is asymptotic at 0. Well, what you're being asked to do is to calculate the area from basically this asymptote up to 1. Right, so this is an asymptotic at x equals 0. Right, so this integral has an infinite discontinuity at the lower bound. Okay, it's infinite discontinuity at the lower bound. So basically what that means is if we were to try to plug in this lower bound, we would get some kind of an infinite discontinuity. Okay, so that's a problem. Right? The fundamental theorem of algebra says that we can't do this because the fundamental theorem of calculus says we can't do this because this function is not continuous on the interval 0 to 1, in particular at the end point. Okay, and of course you can imagine the other scenario where the end point has a discontinuity, would look just, kind of the reverse. Right, so if I want to calculate the integral from a up to 0 in this case, I got a problem with that upper limit. Right, we've got a discontinuity here. Okay. All right, so that being the case, then the third type is where you've got an infinite discontinuity anywhere in between. Right, and so that's kind of the example we led with. Maybe you've got something like this, and you've got a function that does normal things on the outside here, kind of maybe it comes down and hugs the x-axis. And I've got a region from A to B, and in between it, I've got this asymptote. Right, so asymptotic here. Okay, so how to deal with this? What do we do? Well, here's what we're going to do. So let's just push this up a tish here. So here's how we'll approach it. So how to approach these. So the first thing, right, so if f is continuous on the interval a up to b, and has, an infinite discontinuity at b, right? Hence the half-open interval. So if f is continuous on the interval a up to, but not including b, and has an infinite discontinuity at b, right? Then here's what we're going to do. The integral from a to b of f of x dx, what we're going to do is we're going to say that's equal to the limit as c approaches b from the left of the integral from a up to c of f of x dx. Okay, so think about it like this. Here's the picture. Right, we've got asymptotic behavior. Here's your A, and the function is asymptotic at B, right? It has a vertical asymptote at B. So what we're going to do is we're going to inject some other value C, and we're going to calculate this area, and then we're going to let C approach B from the left, right? So obviously this area is going to grow, and this limit will capture the value. Does that make sense? Hopefully that makes sense, right? That's the idea, right? So we'll calculate from A up to just C the normal way, and then we'll let C approach B. We'll let that upper bound approach B, which is some kind of an asymptote, vertical asymptote. Okay, all right, we'll do an example in a second. Let's just bang out the other two cases. They're all kind of similar, right? It's more just writing them down formally. But the second situation would be when if F is continuous on the half open interval from A up to B and including B, right? So half open, and has an infinite discontinuity at A, right? Then we're going to do the same thing. So here we've got A up to B of f of x dx, right? A is problematic, so we're going to take the limit as some other value C approaches A from the right of the limit of the integral from C up to B. Okay. Right, so this is the same idea as what we just talked about. It's just on the other side, right? So I've got some function, right? Some function, this is x, this is my f of x. Right, now I'd like to integrate from A to B, right? But A is an asymptote, a vertical asymptote. So i.e. the function has an infinite discontinuity at A. So what I'm going to do instead is I'm going to drop some C in here, and I'm going to calculate this integral. Then what I'm going to do is take the limit as C approaches A, right? And so as I do that, the integration region, the area will be kind of blown up to the true area of the whole region from A to B. Okay, so it's exactly the same as item 1. It's just literally just flipped. It's the lower bound that's problematic now. And then the third case is, well, what if you have something in the middle, right? If f is continuous on the interval AB, except for some C, right? Right, so some C inside that interval that isn't the endpoint, right? Where f has an infinite discontinuity. So if f is continuous on the interval AB except for some C and B, where f has an infinite discontinuity, well, then we're going to do something real similar, right? So we've got the integral from A to B of f of x dx, and so what we're going to do is we're going to break it apart. We're just going to break it apart into the integral from A to C of f of x dx plus the integral from C to B of f of x dx. Right, now C is the problem area, right? So basically we're going to use 1 and 2 here. Let me explicitly write it down. So this would be like plus equal to the limit as C, let's see, or as, well, I'm going to think of another variable here. So we'll just put D. D approaches C from the lower side of the integral from A to D of f of x dx plus the limit as let's see, f approaches C from the right-hand side of f up to b of f of x dx. Okay, so I'm just kind of breaking that up. I mean, this other piece probably didn't need to be stated. You're going to treat each of these basically like this is case 1, this is case 2, just add them up, right? But you can see the idea here, right? A and B are fine. It's this in-between point where you have an asymptote where you're going to have to do this kind of limiting evaluation, right? You're going to have to evaluate using a limit at those points. Okay. All right, very good. Let's do an example of these. Let's do some examples. Make sure we understand how this works. It's relatively straightforward, but though you can get lost in the details. It is possible to get lost in the details here. Okay, so let's evaluate this integral, 0 up to 1 of 1 over the cubed root of x. Okay, so the issue here is that this function, 1 over the cubed root of x, has an infinite discontinuity at 0, right? You can see that just by looking at this, that if I plug in 0 directly, I get 1 over infinity, right? So we have a problem. Okay, so let's see how we can deal with this. So the integral from 0 up to 1 of 1 over the cubed root of x dx is equal to, it's equal to, right? So we need to deal with this lower bound. That's the problem. So the limit as b approaches 0 from the right-hand side of the integral from b up to 1 of 1 over the cubed root of x. Okay, let's draw a picture just to make sure that this is really clear, like what's happening. All right, so this is kind of looks like this. Right, now here's your 0, and maybe your 1 is somewhere up here. This isn't an exact drawing, right? But you can see that as we get close to 0, you know, this denominator is going to grow, right? And as, you know, when x is 200 billion or something, the cubed root of 200 billion, 1 divided by that number is a very large number, right? And so this the value of this integrand is growing without bound as we get closer and closer to 0. So we have to deal with that, right? That would mean is there's a discontinuity there. And so this is the setup, right? We have to deal with this problematic lower bound. And so the way we do it is we swap in a b, and we're going to take the limit as that bound heads towards the problematic point, right? Because we can't do direct evaluation there, so we're going to have to use a limit argument. Okay, and so the limit as b approaches 0 from the right. Now, can we integrate this? Let's write it slightly differently. Instead, let's write x to the negative 1/3 power. That's a really easy limit, or easy integral to deal with, right? The limit as b goes to 0 from the right-hand side of this is going to be what? X to the 2/3, so it's negative 1/3 plus 3/3, so 2/3 over 2/3. And it's going to be from b up to 1. And what do we get here? We get 3/2, and then it's basically 1 to the 2/3, just 1, minus b to the 2/3. Okay, now what happens here? Well, we can see what happens, right? The 3/2 is just going to be there for sure. And then you're going to have a 1. And then what happens when b goes to 0? Well, this term goes to 0. There we go. Okay, so here's an example of, you know, we've got a finite integration region, but on the lower end of the region, the values do tend towards infinity, right? But even given that, we still can see that the area is a finite value 2/3, or sorry, 3/2. 3/2. Very cool. Let's do an example, another example. Let's see here. Yeah, this is a good one. Evaluate the integral from 0 up to 2 of 1 over x cubed. Okay, so here again, right? At 0, we have a discontinuity. The function has basically an asymptote at 0, vertical asymptote, very similar to the previous example, actually. So the integral from 0 to 2 of 1 over x cubed dx is equal to the limit as b goes to 0, right, from the right-hand side, because we would be going from 2 down to 0, so right-hand direction, of b up to 2, and this we'll write it as x to the negative third power. Okay, so the limit as b goes to 0 from the right of, can we integrate this? Sure, it's negative 1 over 2x squared from b up to 2. And what do we get here? We get negative 1/8 minus negative 1 over 2b squared. All right, very good. Now what happens here? Well, the negative 1/8 is going to be negative 1/8. But then what happens over here? Well, as b goes to 0, this ratio explodes, right? It gets larger and larger, and so this one is infinite. All right, very good. Okay, so that means that this integral is infinite, has an infinite value. Okay. How about we finish up with kind of a harder case? Let's see. Get a new sheet here. We'll do one more example, and this is an example where we've got a doubly improper integral. So the integral is doubly improper. So let's evaluate the integral from 0 up to infinity of 1 over the square root of x times x plus 1. Okay, so this is improper in the sense that, well, we've got an infinite upper integration limit. Okay. We also have, a problem at 0. Right, so we have a problem at 0, meaning this lower bound is problematic as well. Right, here we have an infinite discontinuity. Okay, so we've kind of got two problems here. So to do this, to evaluate this, we will split the integral just at a convenient point. And we'll say x equals 1. It's convenient. Okay, just because it's convenient to evaluate things at 1. So the integral from 0 up to infinity of 1 over the square root of x times x plus 1 dx. Okay, this is going to be equal to the integral from 0 up to 1 of 1 over square root of x times x plus 1 plus the integral from 1 up to infinity of 1 over square root of x times x plus 1 dx, right? So basically just taking that range 0 to 1 or 0 to infinity and breaking it apart into two pieces. Now, in this piece, the problem is the infinite discontinuity at 0. Okay, so that's the problem over here, which we can deal with using the techniques we just learned. And then on this piece, the problem is not an infinite discontinuity. The problem is an infinite upper integration limit. Okay, so for this one, we'll use the techniques we learned sort of at the beginning of the section. Right, so two different techniques that are going to be at play here. Okay, so we'll set it up. Right, so here we're going to need to deal with this lower bound. So we're going to set the limit of b as b approaches 0. Right, we have to approach this value from the right. Right, okay, so that's that one. This is just a strict application, basically setting up examples like the two we just did for this. Right, because that's the problem on the lower side of the range. On the upper side of the range, The problem is this upper bound. So what we're going to do is we're going to set the limit as c goes to infinity from 1 up to c. Okay. Right, so, notice this is kind of a hybrid of the cases we've examined so far, right? We've got kind of two different things going on here. So it's doubly improper. All right, very good. Now, can we evaluate this? You bet we can. I've done this one ahead of time just because I didn't want people to get lost in the details of the actual integrand. But this integrand here can be found using A's and U's, right? So this is turns out this is equal to the 2 times the arc tangent of the square root of x. Okay, so you can spend a little time like sorting that out, but that's what you'll find. Okay, so it's from b up to 1, and so it's the same thing over here. Limit as c goes to infinity of 2 times the arc tangent of the square root of x. Over here it's 1 up to c. All right, and so we can plug everything in here. We can plug it all in, and so what we're going to get here is 2 times the arc tangent of the square root of 1. So 2 times the arc tangent of 1. And then it's going to be minus the limit as b approaches 0 of twice the arc tangent of the square root of b. Okay, so that's this. So that's this one. So twice the arc tangent of 1. Just plug in that upper bound, and I pulled that outside the limit as I kind of did that. So I could, technically, like I guess you would evaluate this first and it'd be the limit of all of that, but knowing that b is not a part of this, I just pulled that out as the same step. Okay, so then it's plus this other piece. All right, now this other piece is the limit as c goes to infinity of twice arctan of square root of c. Like so. And then minus this other piece, minus twice the arctangent of the square root of 1, which again is just 1. Okay, so that is perfect. All right, so then what are all of these values? Okay, so it turns out that, wait 1 second, let me make sure I'm looking at this right. Turns out that, so this one is pi over 2. Sorry, it's 2 times pi over 4. I should be really thorough here. Arctangent of 1 is pi over 4. And over here, it's the same thing, right? So this is also going to be 2 times pi over 4, right? So arctangent of 1 is pi over 4 times 2, right? So those two are both the same, right? And you're subtracting, so they're going to disappear. Okay. And then what's happening inside here? Well, here, b is going to 0, so that means 2 times the arctangent of 0, right? And so this is actually going to go to 0 here. Okay. And what about this one? So this one is going to 0. What's going to happen here? So as c goes to infinity, in square root of c goes to infinity as well. So this would be 2 times the arctangent evaluated very far out on the right. And we know that this tends towards pi over 2, right? We saw that. Right? Keep in mind, I should draw this just because this is such an unfamiliar function for people, right? So this is that arctangent function. So you have negative pi over 2 and positive pi over 2, and the arctangent goes like this, right? So as x goes out to positive infinity, we get ever closer to pi over 2, right? So this guy is heading to pi over 2. Oh, sorry, it's twice pi over 2, actually, right, because of the 2. So all in, what we have here is 2 times pi over 4 for the first one, minus 0 for the second one, plus 2 times pi over 2 for this third piece, and then this last one is minus 2 times pi over 4. All right, so obviously you got pi over 2 minus pi over 2, and then in the middle you've got just a pi, right? So this whole thing is equal to pi. So this area is finite and equal to pi. Right, so just to bring that all into focus here, the integral from 0 to infinity of 1 over square root of x times x plus 1 is equal to pi. Remarkable. Okay, so that's pretty cool. All right, and so I think that'll do it for improper integrals. Okay, so in the next section, when we get back together, we'll be switching gears and heading into section 4 of Calculus 2, which is going to be, we're going to leave behind integration and differentiation for a little bit. We're going to talk about infinite series and sequences and convergence, and it's going to be kind of a different world. So very cool. I know, like Calculus 2 is one of those courses, like typically 5 credits as an undergraduate course, and it is a brutal long list of topics, and fortunately it does shift gears a couple of times, and so this is a kind of a I find that this is a sort of refreshing gear shift, or like direction change a little bit. I mean, we still will be using integrals and and derivatives and whatnot, but it's a little bit of a different kind of mathematical thinking than what we've been using to this point in the course. So, all right, we'll see you all in the next one. Take care.